when is d psi d phi the conderivative is a continuous unitary group. And the result is a theorem by Pedersen plus Takesaki. And if there is time, I will try to prove also a theorem of Kohn that the correspondence between, so phi is a fixed NSF weight, and the correspondence psi goes to the psi phi t. Here you have weights, NSF weights, and here you have unitary cocycles. This is a bijection. So every cocycle appears as the Kohn derivative of some weight. Before going into these things, I will recall or just present several things to say A and also B and also A sub k be positive self-adjoint operators. Then, what means that A is less than or equal to B? Say, by definition, this means that 1 plus A to minus 1 is bigger than 1 plus B to minus 1, which is the same thing as saying that the domain of B1/2 is included in the domain of A1/2, and we have that A1/2 psi is less than B1/2 psi for every psi in the domain of B1/2. Or, if we introduce the notation A sub epsilon, it's equal A times 1 identity plus epsilon A to minus 1. This is the same as A epsilon is less than B epsilon. They are bounded operators for every epsilon bigger than 0. So this is what means this relation for unbounded positive self-adjoint operators. The second thing is what means that a sequence or a net of positive self-adjoint operators converges increasingly to a positive self-adjoint operator. This is, by definition, the fact that, again, 1 plus ak to power minus 1 converges decreasingly to 1 plus a power minus 1. And this is the same thing as ak sub epsilon converges to a sub epsilon for every epsilon bigger than 0. Now, these are elementary things concerning unbounded operators, and a detailed proof of this you can find in modular theory in appendix, page for this. Okay. Let me let me say also the following things, that for a single A sub epsilon converges increasingly to A when epsilon goes decreasingly to 0, and also if you denote by E sub n the functional calculus of A, then also AEN converges increasingly to A. Okay. Now, with these things pointed out, I will take an NSF weight, phi, an NSF weight on the von Neumann algebra M. And let me recall the following thing, that M phi, the centralizer of phi, is the fixed points of, so x in M, such that sigma t of x is equal x for every t, and also is the set x in M such that x times M sub phi is included in M sub phi. M sub phi x is included in M sub phi, and phi of xa is equal phi of ax for every a in M sub phi. Okay. So that given an element, a positive element, 0, bigger than 0, bigger than a positive element A in M phi, that means in the centralizer, then we can define another weight, phi sub A of x, which is equal phi A 1/2 x A 1/2 for x in M plus. And this weight is obviously normal, because if x sub xn converges increasingly to x, then a to power 1/2 xn, a to power 1/2 converges increasingly to this thing. So this is a normal weight. And also, because we have this thing, we have that the M of phi is included in M of phi A. And moreover, because of that, we have that phi A of x defined as here. It's equal to phi of AX plus phi of XA. And this fact says that the new weight, the phi sub A, is also a semi-finite weight. Okay. Concerning the fightfulness.
You don't take 1/2 of that?
Sorry?
You don't take 1/2, otherwise.
I took 1/2 here.
No. One below.
Phi of Ax is itself Phi of x.
And the Px
Both terms are equal to Phi A.
So that this is the definition, right?
Yeah, so
Okay.
that is equal to Phi of xa or Phi of Ax.
It's equal to phi of this times this, but this I can put it in here.
Yeah, that's
So
fine.
it is, what is the first term, the second equation?
Here.
Yeah.
Yeah.
The plus
So what
sign
you
is
prove-
either equal or divided by 2. Yeah.
Thank you. Thank you. Okay. Right. Okay. Now the support of phi sub A is equal to the support of A, as can be checked very easily. Moreover, if A is invertible, then the automorphism group sigma t phi a of x, it's equal to a to power it x sigma t phi of x a to power minus it. Now, this equality can be checked using the KMS condition. However, in the original paper of Pedersen and Takesaki, it is given a direct proof, which is very instructive because you take again the whole construction in order to see this thing. But using the KMS condition, this follows at once. Okay. Good. Now, if you have A and B in M phi, in the centralizer of phi, and both of them A is bigger than 0, B is bigger than 0, then you have that phi sub A plus B is equal phi of A plus phi of B, which, looking at this equality, it's obvious. Still, it is not so obvious because you have to check for x for A plus B. You have to check. This is obvious for A and B invertible. But if A and B are not invertible, then there is a small trick to prove this thing. I will not enter into the details. The details, you have them in the notes, for instance. Okay. This means, so I have that phi A plus B is equal phi A plus phi B. This implies the fact that if A is less than B, A and B are always in the centralizer. Then we have that phi A is less than phi B. This is an obvious consequence of this one. And actually, if AI converges increasingly to A, then also phi sub AI converges increasingly to phi sub A. Here the argument is easy. First of all, the sup of phi sub A over A of x is less than phi, A sub I, A of x, because for x positive element, because of this fact. It's obvious. And now the converse thing is the following. You have that AI power 1/2 x AI power 1/2 converges sigma weakly converges to A x A 1/2 x A 1/2. And because the weight is normal, that means is lower semi-continuous, it follows also that phi sub A of x it's equal to the inferior limit over I of phi I of x, which is less than the sup of phi I of x. So that also this thing is easily proved. Okay. Now, consider A positive self-adjoint operator which is affiliated to the centralizer of phi. Good. Then take A sub epsilon, it's equal A times 1 plus epsilon A minus 1, which converges to A when epsilon is going to 0. and denote also by E sub n the characteristic function of 1 over n of A. Okay. This converges to the support of A, which was not, well, in general, A is not supposed to be with the support equal to 1. That means they're not supposed to be, say, invertible as a non-bounded operator. Non-singular is the word. Okay, and then we have that A epsilon and En as parts of the functional calculus are both in M phi, in the centralizer. And A En, it's equal, is a bounded operator and belongs also to En M En. And here, this operator is invertible. In En M En. Okay. Now, phi sub A of x is defined in the following manner. By definition, we have is the sup when epsilon is bigger than 0 of phi sub A epsilon of x, which is the same thing as the limit when epsilon is going to 0 of phi A sub epsilon of x. Of course, for x belonging to m plus. So that being a supremum of phi sub epsilon of normal functional, this is also normal. Phi A is normal. Okay, then you see the following thing, that if x belongs to En M sub phi, well, from time to time I remember that phi is a weight. So in general I will not take care of this, but from time to time I take care of this and I put, so that Em is M sub phi intersection with M plus En. This is included. It's included in M sub phi intersection M plus. That's obvious because En is in M phi. Then this is included in M phi A epsilon, En, I'm sorry, intersection with M plus. Is by the definition which was given here for bounded operators. And this implies the following thing. This implies that phi sub A of x it's equal to the limit by the definition. Limit when epsilon is going to 0 of phi sub A epsilon of x. But this is phi of A epsilon to power 1/2 times x times A to power 1/2. But x is under En, so I can put the En in here. So that this will be the limit of an epsilon tends to 0 of the following thing, phi of, that's again an easy thing, is A epsilon En to power 1/2 x A epsilon A epsilon En to power 1/2, which is phi A En of x. And because x was in here, that means in here, it means that this is less than infinity. This accounts for the fact that phi sub A is normal and is also semi-finite. Moreover, if you have the support of x times the support of a is equal to 0, then obviously phi sub a of x, you will get inside a 1/2 x, but if this is 0, it means that this is equal to 0. And hence you have that the support of phi sub a is less than or equal the support of a. But actually what we have here, and I will put it in here as the support of phi sub a is equal to the support of a. And now let's see this thing. If phi sub a of x being a positive element in M, is equal to 0, that means that phi a epsilon 1/2 x a epsilon 1/2 is equal to 0 for every epsilon positive. And that means that x a epsilon is equal to 0 for every epsilon. And as a sub epsilon converges increasingly to a, it means that x a is equal to 0, so that x times the support of a is equal to 0, and this accounts for this equality in here. Okay. Good. It's good to have also, but I will write here. It's good to have also the following equality, namely phi sub a of x star x, it's equal to pi phi of a to power 1/2 j phi x phi norm phi to 1/2. Well, pi phi is Gennes representation, and doesn't matter A is an unbounded operator, you can transport an unbounded operator by an isomorphism. You just transport its spectral scale, and you reconstruct this from the spectral scale. Well, this is valid for every x in the n sub phi. And this is obvious because it's more or less obvious because we had an equality 2 lectures before. Namely, this is the limit when epsilon is equal to 0 of phi a epsilon 1/2 x star x a epsilon 1/2. It's equal to the limit when epsilon is going to 0 of phi of a epsilon x star x, because a is in the centralizer of phi. And this is equal to, further, the limit when epsilon is going to 0 of x phi times x a phi again is the adjoint of this, it's phi in the adjoint of this times this, so that the equality is obvious. So that this is equal to further width, and this is the equality. I will remember that we did it, is the limit when epsilon is going to 0 of x sub phi j phi sub phi of a epsilon j phi of x phi. When we found the germ of the KMS condition with the analytic extension of the modular orthogonality group, we proved also such an equality, like here. And this is further equals, of course, it's pi phi of A to power 1/2 j phi x phi phi square. Okay. Now, this was the construction of the weight phi sub A for A affiliated to the centralizer of phi. Now, let's see some properties of this construction, analogous with what we did when A was bounded. Namely, the first proposition is the following, that A is less than B if and only if phi A is less than phi B. And this is clear on one side. This implies that A epsilon is less than B epsilon for every epsilon bigger than 0. That means that phi A epsilon is less than phi of x, so phi B epsilon. We proved it for bounded operators like is here. And this is for every epsilon bigger than 0. And this implies that phi sub A, which is the limit of this, is less than phi sub A. Conversely, assume that phi sub A is less than phi sub B, and take an epsilon bigger than 0. Then, and also take Fn is the characteristic function of 0 n of B, and an x in n sub phi. Looking at what we did upstairs, it follows that, we have the following thing. Pi sub phi of Fn A epsilon Fn, j phi of xv, j phi of xv is equal to phi sub A epsilon of Fn x star x Fn, which is less than phi sub A, and phi sub A is less than phi sub B. So that this is less than phi sub B of Fn x star x Fn, and this is equal to pi phi of B Fn times Jx phi, again Jx phi. Okay, what we proved in here is the following. It's the fact that Fn, A epsilon Fn, is less than B Fn. Now, Fn is going increasingly to the support of B, which is bigger than the support of A. So that we conclude that A epsilon is less than B, so that A, which is the supremum of A epsilons, is less than B. So that the first assertion here, I put such a thing here, it's proved. Okay. The second property is the following, that A sub I converges increasingly to A if and only if phi sub AI converges increasingly to phi sub A. That means for every x in M plus. Okay, if you have this thing, you have also that A sub I of epsilon converges increasingly to A sub epsilon. This happens for every epsilon bigger than 0. And so what we have that phi sub A of x, which is the sup by definition after epsilon, following epsilon bigger than 0, of phi sub A epsilon of x. It's equal to the sup epsilon sup over I of phi A I sub epsilon of x. And this is less than the sup of phi sub I of x. Sub I of x. Okay. So that we prove that the sup of this is less than, we proved that phi sub x, phi x, it's less than the sup in here. And now what we have to do is suppose that you have this condition. Because of this proposition here, it follows that A sub I is increasing because of this proposition. This is increasing. Is increasing to some B by the, and then it follows that phi sub I, the sup phi sub I, it's bigger than, it's less, it's bigger than phi sub B, as we proved in here. Okay. Excuse me. That the fact that this is less than phi sub A of x, this is obvious. So we proved here the equality. Phi sub A of x is equal to the sup in here. So the sup in here will be equal to phi B. But the sup in here was assumed by hypothesis that this is phi sub A. So I have phi sub A is equal to phi sub B. From this, it follows that A is equal to B, right? So that we had also the second assertion here. A third assertion is that sigma t phi A of x is equal to A to power IT sigma t phi of x A to power minus IT. Well, the same equality was already seen by the KMS conditions to be true for A bounded. The passing from A bounded to A unbounded is just a simple exercise with the A epsilons and so on. Okay. Now, from this, it follows that the conderivative dphi I, dphi t is equal to A to power IT. How follows this? You just take the so to say the balanced weights theta of phi and phi, and on the other side you take theta of phi and phi sub a. Okay, then what happens here is that theta is equal to, that tau is equal to theta sub b, where b is the operator 1, 0, 0, a. Okay, hence, it follows that sigma t tau of an x in the matrices 2 by 2, it's equal to b power it sigma t theta of x b to power minus it by the form of this element. And then, sorry, I have this equality by this statement. And then, looking in here, you look b to power it, it's equal to 1, 0, 0, a to power it. And then take in this equality x, it's equal to 0, 0, 0, 1. Well, take the support of a if you don't want to have a non-singular. And once you get x in here, you get exactly the statement I announced. Notice that from this equality, so that from this thing, it follows again that phi a is equal to phi b, implies that a is equal to b. This was proved here, but it follows also from here, where we didn't use this one. Okay. Now, we have the following theorem. You will be astonished at how simple is the proof. A theorem which is a theorem by Pedersen and Takesaki. Also, the construction I presented here is called the Pedersen-Takesaki construction of phi sub a. And so, you have phi, an NSF weight. You have psi, normal, semi-finite, both weights on M. Then the following assertions are equivalent. First is that psi is invariant to the modular automorphism group of phi is equal to psi. The second thing. The second assertion is that the conderivative d psi over d phi times ht belongs to the centralizer of psi. The third assertion is that the same concocycle d psi of d phi t belongs to the centralizer of phi. The fourth assertion is that the concocycle d psi d phi t is an SO continuous one-parameter group. And the fifth condition is that there is a positive self-adjoint operator A affiliated to M phi such that psi is equal to phi sub A. Okay. I will add a sixth condition when I assume that also psi is phi full. And this is phi proposition to sigma t of psi is equal to phi. The equivalence between 1 and 6 follows obviously from the equivalence between 2 and 3, because they are symmetric with respect to phi and psi. So let's prove this thing, and I will assume that the support of psi is equal to 1, that also psi is frightful. Let's see why I implies 2. For x in M plus, we have the following thing. Psi of x is equal to Gesundheit. To the one who sneezed, I said Gesundheit, yeah. Psi of sigma t psi of x, that's obvious. And this is equal to psi of ut sigma t phi of x. Ut, excuse me please, I forgot to say that I denote by ut d psi d phi t. So this is a notation that will be used all the proof. Okay. This is equal to psi of sigma t phi of sigma minus t phi of ut x sigma minus t phi of ut star. And this is equal to, because of condition 1, this is equal to psi of sigma minus t of ut x sigma minus t of ut, and I can put a star outside in here. So what we have that this is equal to this. But this means, by the definition by the properties of the centralizer, this means that sigma minus t, sigma is phi here. Sigma minus t of ut belongs to the centralizer of psi. Because psi is sigma t phi invariant, the centralizer is sigma t phi invariant, so it's also sigma t phi of this will be in M psi. But this is exactly ut. And this is exactly the assertion 2 in here. Okay. Now, what I proved that 2 implies 4. Okay. Indeed, from 2, we get that ut it's equal to sigma s psi of ut. Because this is stable to the automorphism group of psi, right? Okay, now what means this? This means us sigma s phi of ut us star. And this is equal to, because of the cocycle property of ut, this is ut plus s. Ut plus s was exactly this thing. You can look at it as us plus t. us star. Oh, this is equal to this. So that ut plus s is equal ut us. So that indeed 2 implies 4, implies that this is a group of unitaries. Now, the thing is that property 3 is equivalent with property 4. Property 3 is equivalent to property 4 because on one side you have if ut belongs to M centralizer of phi, this is 3. Ut belongs then us plus t, it's equal to us sigma s phi of ut, but sigma s phi of ut, it's equal to ut, it's equal us ut. So that indeed 3 implies 4. It remains to prove the converse, and the converse is equally simple. Namely, if you have us ut, it's equal us plus t. This is in general equal to us sigma s phi of ut. You cancel, and you get that ut is invariant to sigma phi. So that indeed I have 3 is equivalent to 4. Now 4 implies 5. 4 implies 5 because if this is a unitary group, SO continuous unitary group, by the Stone theorem you have that d psi d phi t is a unitary group, so it's an A times IT, power IT. Okay, and then if you have this, this is also equal to d phi A d phi. And this implies, because the cocycles with respect to d phi are equal, it means that indeed psi is equal to phi sub A. Okay? Good. Now, to see that 5 implies 1, the first thing, I will write a little bit more roughly the things. I will not go to the A epsilon and so I will just use A as it would be bounded also. So you have the following thing. Phi sub A of sigma t phi of x it's equal to phi of, let's say, A to 1/2 sigma t phi of x A to 1/2. This is equal to, because A is in the centralizer, then okay, then I can put sigma t phi, I can put the sigma t phi in front of all this. So that this is phi sigma t phi of A 1/2 x A 1/2. This disappears because phi is invariant with respect to its modular automorphism group, and this is equal to phi sub A of x. Good. So indeed, this psi phi sub A is invariant with respect to the group, and this ends the proof, which is a very nice, very clever proof, and a rather simple one. It is from here to here. Yes, so, okay. There are several corollaries of this.
Just one question.
Yeah.
In your proof of 3 implies 4,
3
cancel the UT.
Yes. I cancelled US's.
That's right, but if the statement is for C not necessarily faithful,
No. I said at the beginning I do the proof only in the case of faithful. Psi faithful. For psi not faithful, having a support, you have just to write some more symbols. It's the same thing actually. But what I did here, I considered that US are unitaries. So that's...
Yeah, but I was just going to ask what you do when US...
No. When psi is just normal semi-finite and not faithful, the same proof holds, but you have to put a support of psi somewhere. And even the automorphist group, sigma t psi, then it is just an automorphist group of the reduced algebra of M by the support of psi. So you have to go inside this. But these are very easy things. And I prefer it for the clarity of the proof to have also this a faithful state. And then the proof is really extremely neat. Okay. Now let's see some consequences of this. A first consequence would be the following. Consequences. Right. Suppose phi is a trace. NSF trace. And suppose psi is a normal semi-finite weight. Well, faithful weight. If you want to have faithful, but it's not necessary. Then it's the sigma t phi, it's equal to the identity, because phi being a trace, you have phi of xa, it's equal phi of ax, and this means for every x in M sub phi, and this implies that A is sigma t phi of A is equal to A. So is the identity. As this is valid for every A in M, it follows that sigma t phi is the identity. And of course that then you have psi is sigma t phi invariant. So that in this case M phi is the whole M, and what you obtain that there is a positive self-adjoint unbounded operator affiliated to M such that psi is equal phi sub A. Such a result for psi, a normal positive form, was obtained by Irving-Segal. I would say 1950s or even 1950. Okay, so we got one of the classical results of a second, so that if as a trace NSF weight, then phi is equal phi sub A with A affiliated to M. Okay. A second result, a very nice result, is the following. The following thing is, if there exists phi, an NSF weight, such that sigma t phi of x is equal ut x ut star for an SO continuous unitary group ut, then M and NSF weight on M. Then M is semi-finite. Okay, the proof is obvious here. Namely, you take the analytic generator A of the group AT, of the group minus, I put so, minus IT is equal to UT. So I take the analytic generator, the inverse of the analytic generator, which is...
Unitary group in M. Unitary group in M.
Unitary group
UT is
in
what
M.
in M.
Yeah, in M. Thank you. You take this thing, and then you make the psi, which is phi sub A. Then sigma t psi of x it's equal to A to power IT ut sigma t phi of x A to power minus IT, but excuse me, I have to put minus here and plus IT here, because I took A to power minus IT to be UT. No, it's okay. It's okay. It's okay, so it's sigma t psi of this, is this one. And now this is equal to A to power IT UT sigma t phi x ut star A to power minus IT, which is equal to this.
Oh, you don't need a sigma t phi again.
I don't need a sigma t phi, no here, sigma t phi in here. Yeah, here is x. Yeah, here is x, thank you. Here is x, and what I get, this cancel, this is x. So it follows that the modular automorphism group, sigma t psi, is identity for every x, for every t. But that means that psi is a trace, because the centralizer is equal to the whole M. So the centralizer being the whole M, I have psi of xa is equal psi of ax for every a and x. I should say one thing. I hope that Professor Takesaki will accept my words. This was proved in the lecture notes by Professor Takesaki, but the proof in the lecture notes of this result is a horror. It's a very difficult proof in there. But this one is a very clear and very nice proof. Okay, so this was...
There was no theory of weight available.
of course, yeah, yeah.
So I had to work on the bare hand.
Yeah. I will give another corollary, another consequence of this. The following assertions are equivalent. Namely that I, psi, satisfies the KMS conditions with respect to sigma t phi. Second, sigma t psi is equal to sigma t phi. I give the statement in the case that phi psi are both NSF. And the third assertion is that there exists a positive self-adjoint operator affiliated to the center of M such that psi is equal phi sub A. And the proof is the following. 1 implies 2. This is obvious because I can read I in the following manner. The group sigma t phi satisfies the KMS conditions with respect to psi. And then it coincides with the automorphism group of psi. Okay, now that what I 2 implies 3. Okay, of course, psi is sigma T phi invariant, phi is sigma T psi invariant, so there is an element A belonging to M, say M sub phi, M phi, such that psi is equal to phi sub A. And this A is unique, so we have to show that this A belongs to the center. Well, it's affiliated to the center. And this is the following thing. Sigma T phi of x is equal, because of this, sigma T psi of x, it's equal to a to power it sigma T phi of x a to power minus it, because of this thing. And then it follows that a to power it commutes with sigma T phi of x, but this is an automorphism. So it means that a to power it commutes with m. So a to power it belongs to the center of M. And that means that A belongs to the center of M. Belongs this thing. So, actually, you can look at an unbounded operator, positive self-adjoint, either as A to power it as the unitary group, and then the commutation means that the A to power it commutes with that thing, or you make something like A times the spectral projection corresponding to 1 over n, and so on. So that the study of unbounded operators, it reduces to the study of bounded operators.
IA is bounded?
A to power it is in Z of M for every t. That means that A is affiliated to Z of M. Okay. Now, let me how much time do I have? 25 minutes, right? Okay, fine. Okay. So that in this case, the 6 or 5 equivalent conditions will get a name, especially when also the second weight is fightful. Then we will say that phi and psi commute. Or if this is only normal semi-finite, then psi commutes with phi. So this will be for this thing. Okay, now let's recall one thing, that sigma t phi composition with an automorphism sigma is equal to sigma minus 1 composition with sigma t phi composition with sigma. So that if I have that phi composition with sigma is equal to phi, so if phi is sigma invariant, this implies the commutation sigma t phi composition with sigma is equal to sigma composition with sigma t phi for every t. In particular, if phi and psi commute, so phi psi is invariant to the automorphism group of phi, what we get is the fact that sigma t phi sigma s psi is equal to sigma s psi composition sigma t phi for every t s. The point is that the converses, you will expect the converses here. Converses are not true unconditionally. And it's a very instructive example for this, namely, an example. We take in the Hilbert space L2 of R the translations and the multiplication by characters. So you take ut of xi in R, it's equal to c r plus t, and vs of xi in R, it's equal to e to power I s r xi of r. And then you take the generator of the translations, a to power it, it's equal to ut, and the generation of the multiplication by the analytic generator of the multiplication by characters, which is say b to power is, it's equal to bs. Okay, now let's take into account the following thing. Is what Professor Takesaki mentioned, the Heisenberg anti-commutation relations. So that what you have here, you have that Vs ut, it's equal to e power minus its ut Vs. And if you put here a to power, this is b to power is, a to power it, it's equal to e to power minus its, a to power it, b to power is. By analytic continuation, which A is given by the analytic continuation of this group, it follows that you have b to power is times a times b to power minus is, it's equal to e to power s times a. In this thing, just put e to power, instead of it, put a, and then put it everywhere. Well, by analytic continuation, you obtain this thing. And then what happens? You take the following weights. Phi is the trace on B of H, modified by A, and C is again the trace modified by B. And then what you get that because the modular automorphism group of the trace is always the identity, what you get here, you get that sigma t phi is add of ut, while sigma S psi is equal to add of Vs. Because the trace has the modular autonomous group reduced to the identity. Okay, and then this relation here, this relation for every t is satisfied because of this condition. So this means that sigma t phi sigma s psi is equal to sigma s psi sigma t phi, just because of the conditions we have, the condition we have here. On the other hand, we will see that psi is equal to that phi composition with sigma t psi s psi, it's equal to e to power s phi. So that I don't have a commutation like here. Well, to check this thing is very easy. Again, I write a bit roughly. Is the fact that phi of sigma s psi of x is equal to the trace of the trace of a to power 1/2 b to power is, because this is the modular automorphism group. Okay, b to power is x b to power minus is, it's again a to power 1/2. That means this is equal to the trace of x to power 1/2 b to power minus is, okay, a, and then it's b to power is x to power 1/2. So circular permutations are allowed into the trace. And what I did is a circular permutation, putting x being x 1/2 times x 1/2, right? Okay, now this thing, it's equal to, as we've seen here, e to power minus s times a. So this is e to power minus s. It's minus s here. Okay. E to power minus s trace of x 1/2 a x 1/2, which is equal again with e to power minus s trace of a to power 1/2 x a to power 1/2. That means it is phi of x. It is equal to e to power minus s phi of x. And so the converse of these two assertions do not work unconditionally. Okay, I have a quarter of an hour, 13 minutes, right? No, I don't see that thing here.
Could I make a comment?
Of course.
First, that we have existence proof of the trace when the module of the one is linear by one parameter group. Okay, this is the very first constructive proof of the existence of trace. All the ever since the Marian von Neumann time through the Bowden's very tricky but very nice proof, all using certain kind of compactness. But here, this is all you are now literally constructing trace.
Okay.
So only question remains is what happens when you don't have a trace? Then what you have to show is the existence of equivalent orthogonal family of equivalent projection. That can be done through modular theory as well. Okay. Now that's the comment number one. And comment number two, this counterexample for the quasi-commuteness, the modular homomorphism commute, but not the weight themselves. Okay, the example he showed is very, indeed, it's not a special example. This is the generic.
Yeah.
Whenever you have the actual weight, whose modular homomorphism commute, but not does not commuting actually, that does not satisfy this one any of the equivalent conditions. Then when you have a say in a factor case, then the one modular homomorphism give the transform the other exactly way you describe, and type 1 factor, infinity factor sitting inside, and that precisely the example described here is happening.
That's the reason that if you have two weights whose modular automorphisms commute, but they do not commute, one says then that the weights anti-commute.
So if one knows one of phi and psi says is faithful, and one is a finite functional, the bounded functional, then the whole thing is equivalent.
Okay.
It becomes fall into the category.
What I will do now, I will just state some positive results for this. Namely, the first result is that if phi is a state, normal semi-finite, normal fightful state, and also sigma acts trivially on the center of M, which is automatic if M is a factor, then the following are equivalent. First, well, but let me see, sigma goes from G to the automorphisms of M, where M is a group and sigma is a continuous action. Okay. So the first thing is that phi tensor sigma G is equal to phi, and the second assertion is that you have this thing, sigma G tensor sigma T phi is equal to sigma T phi composition with sigma G. So what you have to have here is that this should be a state, a finite weight, and also that this action acts trivially on the center of M. A second result of this form is the following. If phi is finite, or if phi is less than psi, then the converse of this is true. That's the converse of, let me put 2 on this. Converse of 2 is true. So this time is either than phi is a state, as we saw, or if I have a majorization. A third condition is that if phi is NSF and you have an action sigma of G on automorphisms of M, which is with G a compact group, then also these two things are equivalent. And the last result here is that if you have that sigma T phi commutes with sigma S C for every T and S, then what follows, there is some consequence for the states, namely that for the weights, namely that the weight phi plus psi is semi-finite, which is a non-trivial result. Okay, last thing that I would mention is the following thing, which is not about the converse of this, is the fact that for phi psi normal fightful states, the following are equivalent. Namely, that psi commute, phi commute. Second thing is, and the third thing is, first the third thing is sigma T phi composition sigma S psi is equal to sigma S psi composition with sigma T phi. And here is a condition which reminds what means for normal operators to commute. And namely, it is the following thing, that phi plus I psi, which is a complex linear functional, has an absolute value. Is a non-trivial fact of the theory of von Neumann algebras, this polar decomposition of forms. So, and this is equal to the absolute value of phi minus I psi. This kind of result was obtained by Professor Takesaki in the lecture notes when he published it. Now, you must accept of this result, for which I sent to modular theory and references there. These other results are already proved in the notes I will give to you. So that, I thank you very much.